Hello everyone, welcome again. In this part, we will be conducting a simulation study to investigate the performance of the naive and single imputation approaches. We have played with simulated data in the past weeks, but we have considered only a single, let's say, data set. Here, we will be simulating many data sets. So we simulate many data sets with complete data, then we will impose missingness considering the different missing data mechanisms that we have learned, missing completely at random, missing at random, and missing not at random. And for each generated data set, we will apply each of the different strategies: complete case analysis, mean imputation, regression imputation, stochastic regression imputation, and we will check how well each of these recover the true parameters. So let's be more specific. Our context is the following: we will generate 1000 datasets, and each dataset has 200 observations, and data will be simulated from a bivariate normal distribution with the following structure. For the vector of means, we consider 0 for both means, and the variance covariance matrix, the variances are 1 for y1 and y2, and the covariance is 0.5, and this implies that the correlation between y1 and y2 is also 0.5. And then, as I said, we will study the performance of the different approaches, and we will consider the three different missing data mechanisms. So for missing at random, here are the notes, the missing data indicator. Oh, I forgot to set. So we have two variables, y1 and y2 is subject to missingness, okay? And R is the missingness indicator, and it will take the value 1 if the corresponding y2 value is observed, and it will take the value 0 if the corresponding value is missing, okay? So we will have an R indicator for each of the 1000 datasets that we are generating. Okay, so we generate 1000 datasets, many datasets. For each dataset, we will impose missingness. So we will have an R indicator for each dataset that we have generated, and then we will apply our methods to each dataset as well. And so we will have a bunch of estimates, and at the end, we will collect everything together and look at different quantities or different properties, okay? And so missing completely at random, so the probability of y2 being observed is 0.5. Here it's missing at random because the probability of y2 being observed only depends on y1, which is fully observed, and I've selected these two parameters. And finally, for missing not at random, the probability of observing y2 value depends on both y1, which is fully observed, but also depends on y2, that as the variable that has missing values, and so it's missing not at random. And yes, as I said, the goal of this simulation study is to investigate the performance of the complete case analysis and the single imputation mechanisms that we have learned. I haven't considered OTDEC is more specialized, so we will be looking at complete case analysis, and then from single imputation, mean imputation, regression imputation, and stochastic regression imputation. And we have several quantities here, right? And because y2 is the variable with missing values, I will be looking at how well the different strategies can recover the mean of y2, the variance of y2, the correlation between y1 and y2, and I will always be interested in looking at the lower and upper limits for the confidence interval for the mean of y2, because y1 and y2 jointly, they are normally distributed. I know that the marginal is normally distributed as well with this parameter. So I know from stats 101 that a confidence interval for the mean takes this form, okay? And where n is our sample size and t stands for the t distribution, and this quantity t of n minus 1 are the degrees of freedom, okay, of the t distribution, and here is the quantile for the 95% confidence interval. Basically, that's it. And here are the estimates of the mean and of the variance, so the sample mean and the sample variance. Okay, so for each of the 1000 data sets, I will impose missingness, and then I will be interested in looking at the estimated sample mean, the estimated sample variance, the sample correlation, and the lower and upper bound of the interval, right? The estimated after imputing the missing values with each of the single imputation mechanisms, or by considering complete case analysis where I'm ignoring the contribution from the individuals with missing values, okay? And okay, so let us start. And what have I done? There are many ways of doing this. I've tried to be at least organized. I'm not the most efficient programmer. I don't claim to be, because I know I'm not, but I've tried to be organized not to mess up everything. So, okay, here I'm specifying the means, mu1 and mu2, the variances, the correlation, and here I'm constructing manually the variance covariance matrix. This is similar to what we have done before. So I need to load the package mass to allow me to simulate from a bivariate normal distribution. And now I'm simulating. I'm saying that and sim, this variable, stands for the number of simulated data sets, 1000, and n for my sample size, the sample size of each simulated data set, 200, and I'm storing y, the data set that contains information on y1 and y2 in an array with n rows, to columns. So an array, I can think of several matrices, right? So I have 1000 matrices of uh, with n rows and 2 columns. And then, because I'm interested mainly on y2, because I want to estimate the mean of y2, the sample variance of y2, and the correlation and the lower and upper bound of the confidence interval for the mean of y2, after imputing the values using the different strategies. So I'm storing the values of y1 and y2 in separate variables, okay? And here I fix the seed to be 1, I mean, just because it's the first number, right? Not because the results depend. Here we are simulating a lot of data sets, so we shouldn't see many differences across the seed, and the sample size is kind of reasonable. So, but yeah, it's my preferred seed only. And okay, this is exactly what I'm doing. And then I'm storing y1 and y2 now are matrices, right? Because y they both have they both contain n values over and sim data sets, right? So the first column of my matrix y2 corresponds to y2 in the first generated data set, the second column, the values of y2 in the second generated data set, and so on and so forth. Okay, so I will read this. That is okay. And now I will start with missing completely at random, okay? And I know that I have here auto-impose. The probability of observing a value is zero 0.5. I know from past lectures and workshop that I can use the r binom function. I just need to set the argument size to 1, and my probability is here 0.5, okay? Then if I do this, it is okay. And now what I have done is to try to make things a little bit more organized, is to create a function that will take as inputs our data separately, in this case y1 and y2, the generated missing data indicators, and an argument that stands for the method that we want to use to impute the corresponding missing values, where CCA stands for complete case analysis, ME for mean imputation, RE for regression imputation, and not EI, stochastic regression imputation. Okay, and then I just said, okay, I will use if the method is complete case analysis, and I'm storing the results. I'm interested in 5 quantities, right? The mean of Y2, the variance of Y2, the correlation between Y1 and Y2, the lower limit for the confidence interval for the mean of Y2, and the upper limit. So these 5 quantities, okay? And I have created a matrix that has n rows. So each of the rows is storing one of these quantities. The first row stores the mean, the second the variance, the third the correlation, the fourth the lower limit, and the fifth the upper limit. And then I have NSIM columns, so 1000 columns where I store these quantities for the different simulated data sets, okay? And okay, for complete case analysis, so I'm basically looking at Y2 and just using the values for which the missing indicator takes the value 1, because I know these are the ones with observed values after I have imposed missingness, right? Then I do the same for the sample variance. For the sample correlation, I know that because a complete case analysis disregards the individuals with missing observations. So I know that I also, although Y1 is fully observed, I need to discard those subjects for which the corresponding Y2 value is missing. So that's why I'm only also retaining those with those for which the missing indicator is 1 to compute the correlation. And here I'm computing the lower limit of the confidence interval. And note that here we have n minus 1 for the degrees of freedom, and here square root of n of the sample size. But under a complete case analysis, the sample size only corresponds to those with a missing indicator of 1, and that's what I have here. Then if the method that I specify is mean imputation, what I will look is at this part, and what I will do is, okay, I will create, it's similar to what we have done before. I will create a variable that I have called it here, y2 underscore completed, that will store the values for the completed variable. And here I'm not creating one for each simulated data set. I'm overwriting, right? For every time I change the data set, I change this quantity, and then I compute these things. Okay, so what I'm storing at the end, it's just the different quantities that I'm interested in, not the completed variable. Okay, I could store it, but I'm not really interested on it. So I'm just storing and I'm overwriting this every time I look at a different data set. Okay, so and this is exactly what we have done before. If the value is missing, I compute the corresponding mean. Otherwise, I pick up the observed value. And then it's exactly the same thing. I compute the mean, the variance, the correlation, and here it's the confidence interval. And now we can use the sample size n because we complete the data set, we impute the value. So at the end, our sample size is n. Okay. And the same for regression imputation. Here for regression imputation, I need to do a regression where my response variable is y2 that has missing values, and my observed and my covariate, sorry, is my observed variable is y1, and that's exactly what I have here. And I know that I do that for those with observed data, so I pick up those for which r is equal to 1, and then I've computed the predictions manually. And they are here, right? So it's basically beta 0, it's the first coefficient. We only have 2 regression coefficients, right? Beta 0, the intercept, and the regression coefficient associated to the variable y1. And these are my predicted values. And again, the same thing. If the value, I will create the completed variable where I will store all the values observed and imputed. If it's 0, I will take, if it's missing, I will take the prediction. If not, I will take the observed value, and then it's exactly as we have done before. It's the sample means, variances, correlations, the upper and the lower limit of the interval. And then for stochastic regression imputation, it's exactly what I have in regression imputation, but here in my predictions, I had the random noise, okay? And then I will return. What I want my function to return are the estimates. Sorry, the names are possibly not the best. It's what occurred to me. So I'm returning the estimates of the mean. So mu2 for y2, for the variance of y2, for the correlations, for the lower limits, and for the upper limits. Okay, and that's my function. Let's run it. And okay, I have created my function and I have called the function single underscore imp underscore sim. I mean, it's not only single imputation, we also have complete case analysis, but okay, you can rename it if you come up with a better name. Okay, and so basically I will save the results of the function in an object and then I can extract each of these quantities. Okay. So for the first method, I'm using CCA. So I'm using complete case analysis. So I know that my function will just pick up this bit. Okay. And the same for the other methods. If when I specify method equal to mi, so I will do mean imputation and so on and so forth. Okay. And so let me just run to give you an example. This might take a while. Oh, now it's all the inputs. Okay, let's come here because we have the same, but I can also do something. Okay, so what I have done is I have applied the function using each of the methods that we are interested in, and what the function returns is an object, is a list, and this list has 1,000 estimates for the mean of y2, 1,000 estimates for the variance of y2, 1,000 estimates for the correlations between y1 and y2, 1,000 lower limits for the confidence interval, and 1,000 upper limits, right? But then I will not look at one by one. So usually we do the Monte Carlo mean. For all the means, I have computed the mean. For all the variances, I have computed the mean as well. So I have an idea of what is going on, and that's what I have here, but more beautiful here. And remember that the purpose of doing a simulation study, it's because we know the true value, so we can judge how well the method is performing. Remember that for what we have done in the last video and in the last week, we have an observed data set, so we know that if we impute on the regression line or if you impute on the mean, we are losing variability, and we know that they are not good, but how bad they are or how good they are when they are good, we cannot exactly judge because we don't have the benchmark to compare. Here we have the benchmark because we have simulated the data, so we know the true values that we have used to simulate the data. Okay, so I know that the true value of the mean of y2 is 0, the variance of y2 is 1, the correlation is 0.5, and I've computed the lower and upper bound of the confidence interval, so I can compute the coverage. Remember that the interpretation of 95, say, confidence interval is that, for instance, if I repeat my experiment 100 times, I know that my confidence interval 95 times should contain the true value, right? Here, I can do that experiment, right? Or I can check that, not do that experiment, but I can check that, right? Because I have generated 1,000 data sets. For each data set, I compute the confidence interval, right? I have computed the lower limit and the upper limit. And for each interval, I have 1,000 of them. I can check whether or not the true value of the mean, in this case 0, is contained in the interval. And then I can look at the proportion of the intervals that contain the true value, right? And this gives me the coverage. And I know that if I'm computing a 95% confidence interval, as it is the case here, I know that the coverage should be close to 0.95, okay? And okay, let's start looking at the mean of y2. We know that the true value is 0, and all methods are able to. This is the mean across the mean. So we have computed 1000 means, and then we have computed the mean of these 1000 estimates, okay? And they are all close to 0, and there is no surprise. We know that missing is completely at random, so we know that complete case analysis provides unbiased estimates, mean imputation provides unbiased estimates of the mean, and we are looking at the mean, and also regression imputation and stochastic regression imputation, okay? So everything good. Now let's move to the variance. We know that the true value is 1, and we see that complete case analysis, this is, I have obtained 1000 values for the variances, and I have computed the mean. So it's okay. Mean imputation, bad. We already know that mean imputation attenuates the variability. Regression imputation, the same, because the values also fall on the regression line. And stochastic regression imputation, it recovers the mean well. Now, for the correlation, we know that the true value is 0.5, right? And we see that complete case analysis recover well. The same for stochastic regression imputation. No surprise, we already knew that this should be the case. We are just checking empirically that this is in fact the case. And we know that mean imputation attenuates because the values fall on a horizontal line, the imputed values. And regression imputation also increases the correlations because the values lie on a regression line. So they are all aligned. And now, for the coverage, complete case analysis, good. And wait a minute, because I've told you that complete case analysis is not efficient, and here everything looks good, but just wait a minute, I haven't lied to you. Mean imputation, bad coverage is the worst coverage, right? We are far away from the nominal level. Here we want to be close to 0.95. So mean imputation, bad. Regression imputation, bad as well. And stochastic regression imputation, still not good. So, and this is the problem, this comes from the fact that it's a single imputation. So the variability of the estimators, in this case, the standard error of the mean, they are attenuated, and this has consequences, for instance, in terms of the coverage. So we see that stochastic regression imputation performs well in recovering the mean, the variance, and the correlations, but that the coverage of the confidence intervals is not correct, okay? So when we are providing confidence intervals, so uncertainty measures, they are not correct, okay? Sorry. But let's here we have the mean. This table, what this table summarizes is that for all estimates that I have obtained, 1000 estimates for each method and for each quantity, I have computed the mean. Let's look at the histogram of these quantities rather than just looking at the mean. So this is for the mean of y2, and this is for me for complete case analysis, mean imputation, regression imputation, and stochastic regression imputation. And the red line is the true value, 0. So as we have seen, they are all okay, right? And this is the same, but for the variance, we see that mean imputation does not even come close. Regression imputation is slightly better, but still bad. And stochastic regression imputation and missing and complete case analysis, it's okay. And then for the correlations, the same. And okay, now let's look for a moment at complete case analysis, right? It works well. It's missing completely at random, so we have obtained unbiased estimates of the mean, of the variance, of the correlation, and the coverage of the interval is good. But when it comes to confidence intervals, there are two things that we should look at. It's the coverage, so the coverage should be close to what we call the nominal level. In this case, the nominal level is 0.95 because we are computing 95% confidence intervals, but also we should look at the width of the interval, right? Ideally, the coverage is close to the nominal level, and the width of the interval is as short as possible, right? Because, for instance, imagine the correlation. If I tell you that my confidence interval for the correlation is between -1 and 1, it's possibly not very useful, right? Because these are the natural bounds, let's say, for the correlation. So we want to be as precise as possible. So what I decided to check, and I have told you several times, and I've told you because it's what comes in is what it's said in the literature, is that although in the missing completely at random case, complete case analysis provides unbiased estimate, they are not efficient. And what I have decided to do is, okay, I will compare the width of the confidence interval. So the width is just the upper limit minus the lower limit, right? The way I compute the width of the confidence intervals. Because I have simulated data, I have access to the complete data sets. So let me just compute the width of the 95% confidence intervals for the complete data, okay? And I expect that because I know that complete case analysis is less efficient, I expect the width of of the intervals to be larger for complete case analysis. And this is exactly what I have done for the complete data. And then I have looked at the width. So I have again generated for the complete data set when I have computed 1095% confidence intervals, and then I have looked at the width of each of the intervals, the same for complete case analysis. So at the end, I have 1000 widths for the complete case analysis and 1000 widths for the confidence interval that corresponds to the complete data. Okay, and then I computed the average of the widths. You can look at the histogram, you can play around, and I have that the average width across the 1000 widths is 0.28 for the complete data and 0.40 for complete case analysis. So that goes that aligns with our expectations, right? The width of the intervals under complete case analysis, it's bigger than that for the intervals based on the complete data. But still, okay, we know that missing completely at random is a strong assumption, but complete case analysis, it's good. We have more, we are less efficient, but it's okay, right? But it's missing completely at random. And we know that missing completely at random is a quite strong assumption, okay? Now I have moved to missing at random case. So I will use the generated data that I got from the first case, and then I will impose, the missingness by the way that I'm told before, right? We have been told here that for missing at random, we are considering this here, okay? And okay, if I do that, then it's exactly the same thing. I have generated the missing data indicators, and then I pass to the function y1 and y2 are the same as before. What is changing now is the missing data indicators, okay? And it's exactly the same thing. Now let us look at the results. For mu2, the Monte Carlo mean, or the mean across the 1000 estimates that we have. Complete case analysis, remember that the true value is 0.24, so it's biased. Mean imputation, again, and here it's not a surprise that they are the same, right? We have seen that the mean with mean imputation is equal to the complete case analysis. Regression imputation unbiased, stochastic regression imputation unbiased for the variance. Complete case analysis 0.9, so not too bad. Mean imputation 0.6, bad. Regression imputation 0.75, and the variance under the stochastic regression imputation 1, so it's well estimated. And for correlations, again, all methods provide bias estimate apart from stochastic regression imputation. So as we have been told, stochastic regression imputation provides unbiased estimates even when the data are missing at random of the means, correlations, regression coefficients. Here we are not looking at regression coefficients, but if we were, they would also be unbiased. Again, the coverage is bad, and look at the coverage. Remember that the coverage for complete case analysis and then missing it completely at random was correct. Now look, 0.83. So it's a really bad coverage, and mean imputation is close to 0. Why? This is a biased estimate. The variance is too small, so obviously the confidence intervals basically, or almost any of them contain the true value 0. Okay, and this again, remember that last week I said mean imputation is possibly the worst imputation method, and I think these results show you why, or show that this is uh, the case. This is in fact the case. Okay, so again, stochastic regression imputation, it's good, but it's a single imputation mechanism, so we know that the coverage will be underestimated. It will not be correct, and here I plot exactly the same histograms of all the estimates. So here I have 1000 estimates for the mean under the complete case analysis, and the same for the other methods. And here it's the same in terms of the correlation. Sorry, I'm moving above. Yeah, so it's here it's for the variance missing at random, and here for the correlations. Okay, so now let's go to the most challenging, let's say, case, and we will simulate or we will impose missingness by using we will impose missingness, sorry, under a missing not at random mechanism. And again, it's exactly the same thing that we do. So that's why I have created a function. So once we have created a function, it's just a matter of passing the inputs to the function, and things are more organized as if I was running all the procedures individually without a function. So I think it's a good thing to create a function, but okay, it depends on our own preferences. Now, we already expect that complete case analysis, mean imputation and regression imputation, there are no miracles. They were not good with missing at random, so they will not be good here with missing not at random. But look at stochastic regression imputation. The true value is 0.52, the variance is 1.53, the estimate, and the correlation 0.2, and all the coverage are 0. So none of the intervals for the mean contain the true value 0, right? So missing not at random is hard to handle. That's why most methods focus on missing at random. Nowadays, there are still quite a lot of literature of missing not at random, but it goes with a lot of assumptions. And well, missing at random also goes with a lot of assumptions. But just to make the point that missing at random things are still under control with stochastic regression imputation, and missing not at random, basically none of the methods provide decent or manage to deal with missing not at random method. And here I have the plots of the histograms of all the estimates for the different quantities, and we see that they don't come close to even the true value, most of the values. Okay, and well, as just a final note, this was a simulation study designed to investigate the performance of complete case analysis and single imputation methods. And we have seen that stochastic regression imputation under missing completely at random and missing at random was quite a good method. It had a problem with regards to the precision of the estimates, right? We know that the coverage is underestimated, but it also, and so single imputation is not in general recommended, but it forms the basis of multiple imputation, and in fact stochastic regression imputation forms the base forms the basis, sorry, of one of the most widely used mean imputation methods. So it's good to learn it here. And also, if we are interested in doing inference, of course, single imputation is dangerous and not recommended. If we are just interested for some reason, sorry, uh, in coming up with an estimate for the correlation, for the mean, or wherever, if we do not need to provide like confidence intervals, so we have seen that stochastic regression imputation can in fact be used. But most of the times, as statisticians or data scientists, if we want to be more modern, we need to take uncertainty into account, and so stochastic regression imputation fails in that regard. But if you are just interested for some reason in estimates, point estimates, stochastic regression imputation, it's a good method to consider. And that's it for this part. In the next and last part of this week, we will see how to deal with the case where we have several variables with missing values. Thank you, and see you in the next video.